Hi, everybody. Today we're going to be doing the review for Unit 9, which is stoichiometry. So we're just going to get right into it. This one is 50 questions, so not as much as they normally are. So hopefully we can get through this within an hour. I think we should be able to. Let's zoom in a little bit. All right, let's choose our color, thinking pink. Okay. So what they're asking us to do in number 1, they give us some information, but ultimately they're just asking us to balance this equation. This one is an easy one because if we look over here and I'll draw our little T, I know there's not really that much room, but here's our T method. We've got magnesium, we've got 1, nitrogen, we've got 2 on this side, magnesium, we've got 3, and nitrogen 2. So our nitrogens are good. The only thing is that we need 3 nitrogens on this side. So we literally just need a 3. That is it. These two other substances do have coefficients. They are 1s. You do not need to put them, but they are there. Next question, I'm actually going to use number 1 to help us with number 2. Okay. So if an equation is balanced properly, both sides of the equation must have the same number of what? The answer is going to be atoms. Okay. Let's look at why the other answers don't make any sense, okay? Because this is correctly balanced, okay? Everything is balanced on both sides between the reactants and product side. So moles of molecules, does that have to be equal? Well, if we look on the reactant side, the total moles of stuff that we have is 4 moles. We have 3 moles of magnesium and 1 mole of nitrogen gas. That does not equal what we have on the other side. On the other side, we only end up with 1 mole of magnesium nitride. So moles of molecules does not make sense. Numbers of molecules also doesn't make sense because these coefficients can not only be read as numbers of moles, but you can also treat them as if they are just individual molecules. So if we were to read it like that, this would say 3 molecules of magnesium and 1 molecule of nitrogen makes 1 molecule of magnesium nitride. Now, the numbers of molecules also is not equal on both sides. Coefficients, same thing. So 3 and 1, that's 4 on the reactant side versus just 1 on the product side. That also does not have to be equal. What does have to be equal is the numbers, the individual atoms on both sides. On the reactant side, we have 3 atoms of magnesium and 2 atoms of nitrogen. And we have the same stuff on the other side, 3 magnesiums and 2 nitrogens. So atoms, that is what needs to be equal on both sides in order for something to be properly balanced. Okie dokes. Let's move on. Number 3, which equation is correctly balanced? So let me just zoom in. All right. So if we look at the first one, okay, here on the reactant side, we have 4 hydrogens and we have 2 oxygens. On the other side, we have 4 hydrogens and we also have 2 oxygens because, again, these coefficients distribute into everything inside that substance. So this one off the bat, this is the one that we're going to go with. That is correctly balanced, but let's just take a look at the other ones anyways. So on this side, for choice B, we have 1 calcium and we have 2 chlorines. On the other side, we have 1 calcium, but we only have 1 chlorine. So that doesn't work. On this side, for choice C, we have 2 hydrogens and 2 oxygens on the product side. And on the reactant side, sorry. And then on the product side, we have 2 hydrogens, but only 1 oxygen. So that also doesn't work. And if you go through choice D, you'll also see that that doesn't work as well. It is not balanced. So we would want to go with choice A for number 3. All right. Number 4, what type of reaction is shown above? So I can see that I have this and this. There's a plus sign, meaning that they are 2 separate substances. So I have 2 separate substances on the reactant side, and they come together to form 1 compound on the product side. So this would be considered a synthesis reaction. We are combining 2 things to make 1 larger product. Number 5, what is the gram formula mass of ammonium sulfate, NH4SO4? Okay, so what we have to do, and again, gram formula mass is the same thing as molar mass. Okay, except that they are just asking gram formula, so it could be you can just say it in grams, that's fine. So what we're going to do is we are going to look at all of the atoms. So knowing how to count your atoms properly is important. Otherwise, you won't be able to do this topic. You also wouldn't be able to balance equations properly. So I'm going to write down all of the elements that I see. We have nitrogen, hydrogen, sulfur, and oxygen. Now I have to count everything. How many nitrogens do we have? Well, there isn't an invisible one right here. But this coefficient out here, not coefficient, this subscript out here, this 2 gets distributed into everything inside the parentheses. So it would normally be 1 nitrogen, but it's really 1 times this 2 out here. So we have 2 nitrogens. In a similar way, we also have to distribute this 2 into these hydrogens. So it's 4 times 2. So we actually have 8 hydrogens in total. How many sulfurs do we have? Well, the sulfur is not in parentheses and there is no subscript directly in front of it. So it is just an invisible 1. So we only have 1 sulfur. And this 4 subscript belongs directly to the oxygen. So there are 4 of them. Then what you're going to want to go do, I'm just going to show you where to get it. You want to go to your reference table. When I go here, just don't mind the all the writing for a moment. But if you zoom in, all of these numbers here, those are your atomic masses. Okay, this is the information that you're going to need. Now, a lot of these can be rounded to the nearest whole number. The only thing that I would really tell you to look out for is chlorine, because it's pretty much right in the middle. I would honestly personally round this to 35.5. And same for copper, I would round that to 63.5. So if you see something is really, really close to the middle mark, I would round it to 0.5 instead of, going to the nearest whole number. But aside from that, let's go back to this. So if you were to go and look up all of those masses, nitrogen is 14 grams per mole or 14 AMU. Hydrogen is 1, sulfur is 32, and oxygen is 16. So you multiply all of these out. So you guys will definitely need a calculator for this. And we end up with, when we add all this together, we end up with 132 grams. So we are going to want to go with choice A. All right. Next, the empirical formula of a compound is CH2. The molecular formula of this compound could be what? So in this one, we have to kind of work backwards. So normally you're given a molecular formula, and then you're asked to reduce it to its empirical formula. So what you want to do, if you have an example like this, is you look at the ratio that you are given. So this ratio is 1 to 2. So whatever this empirical formula came from, that molecular formula also has to have this ratio. So let's just go ahead and look at the ratios of the other things of the choices that we're given. So C2H2, that's a 2 to 2 relationship, where if we reduce that, that's 1 to 1. So it's not A. Same thing for B. This is 3 to 3. If we reduce that, it's just 1 to 1. So that also doesn't make sense. C2H4, that is 2 to 4. We can reduce this. Both are divisible by 2. So if we divide 2 by 2, that's 1. And 4 divided by 2, that is 2. So this one does have the same ratio. So this could have possibly have been the molecular formula for this empirical formula. Let's just check the other one. CH4, our ratio is 1 to 4. Yeah, this one doesn't make sense. Again, what we're doing is we're working backwards. So if you had been given originally this is a molecular formula for ethene. And if we had asked you to write out the empirical formula, what you would have done is you would have just taken these numbers, okay? So your ratio right now is 2 to 4, but your empirical formula is always the simplest possible ratio between your atoms. Both of these are divisible by 2, so I can divide these by 2, and then we end up with 1 and 2. And these are then used as your new subscripts for your elements. So it's C1, but we don't write ones, and H2. So this could have definitely been the molecular formula from which this empirical formula originated. All right, let's get rid of all this. So again, you basically just have to make sure that your ratios are the same. All right, number 7. Given the balance equation representing the following reaction, which type of chemical reaction is represented by this equation. Again, this is another synthesis reaction because you have two distinct reactants and they are coming together, combining. That's the key word that you want to look for. They're combining to make one larger product. So again, this is a synthesis reaction. Okay. Given this reaction, they give us a balanced equation. What is the total number of moles of KCl produced when 1.5 moles of KClO3 is decomposed? So this is from lesson 9.5. I'm just going to write it over here. This is concept 3. This is mole ratios. Okay. When you get a question like this, what you should do is just from the actual question, circle the substances that they are talking about in the problem. Okay. You'll notice that they are not talking about one of the things here. They're not talking about the oxygen here. So you can kind of just pretend it's not there. I'm also going to circle these things in the equation, including their coefficients. Those are going to be important for us. Okay. Now this one is kind of easy, but what I'm going to do right now is I am just going to set up one side of my proportion directly from the stuff that I see in my equation. So 2 moles of KClO3 react with 2 moles of KCl. Okay. Now, what we want to do is we want to know what is the total number moles of KCl, which means this is what I don't know. I don't know how many moles of KCl I'm going to need or how much I'm going to get when we only use 1.5 moles of KClO3. Now this one is easy because the ratio between KClO3 and KCl is just 1:1. So if you use 2 moles of this, you'll get 2 moles of this. If you only use 1.5 moles of this, you're also going to get 1.5 moles of this. But if you're not clear on that, you can just go ahead and cross multiply. So you would end up here with 2x equals 2 times 1.5. I'll write all of this out. We can simplify. That's 2x equals 3. We want to divide by 2. And we end up with x equals 1.5. So you can see that we do just end up with 1.5. So in order to make 1.5 moles of KCl, you're going to need 1.5 moles of KClO3. Okay. So again, your first step is to just set up the left side of your proportion using exactly what they give you from the balanced equation. We're going to have quite a few of these in this review. So if we need more practice is coming your way. Okay. Also, I posted individual videos that I just pulled from YouTube on all of these different topics. If you still feel like you're not understanding one of these topics that I'm talking about, you can go ahead and watch some of those videos that I posted. Okay, so this question is a 2-step question, okay? What we first have to do is we have to first figure out our mole ratios. So we're given this balance equation and we're asking how many grams of oxygen are completely consumed in the production of 1 mole of Na2O. Now, they're talking about grams and they're also talking about moles, which means that we're going to have to do a mole to gram or mole to mass conversion at some point, but you can't do that yet because the information directly from the balanced equation is simply talking about moles. Okay, so first what I want to do is, again, I want to circle the things that they're talking about in the problem, which is oxygen and sodium oxide. So from this equation, which again, I tell you guys to kind of think of as recipes. Now, if I'm reading this, there is like an invisible 1 coefficient here. So in order for this recipe to work, you need to use 1 mole of O2, and that will give you 2 moles, or you can think of it as 2 servings of Na2O. Okay, so this again is information directly from the equation. Now, this is what the original recipe calls for. However, we don't want 2 servings of Na2O. We only want 1 serving or 1 mole. So I'm going to use this information that they've given me in the problem. One second, my pen thing disappeared. So 1 mole of Na2O is what we're looking to make. So we're obviously not going to need as much oxygen to do this, okay? So we want to know how much oxygen will we need to do this? So this is just X. So we're going to cross multiply. We can see 1 times 1 is just 1. Equals 2 times X, that's 2X. And now to solve, we just divide by 2. And we end up with 0.5 moles of O2. So in order to make just 1 mole of this sodium oxide, we only need half a mole of oxygen. But that's not what the question is directly asking. They're not asking how many moles of oxygen do you need. They're asking how many grams of oxygen do you need. So they want to know how much does this actually weigh? Okay, so what you need to do is you need to go to your reference table. And right here on the very last page, you are going to use this equation. Okay, so that's what we have to use now. So let's go back. Oops. Okay, so now I'm going to use this equation. And again, I'll just write it out here so we can see it. It's moles equals mass over gram formula mass. Nope, that's not what I want. Okay. So number of moles, we know how many moles of oxygen because we just figured that out. It's 0.2. So that's 0.2. They're asking how many grams. So we don't know what the mass is. And the gram formula mass, you have to figure out. And they're asking about oxygen. Now, oxygen, as you can see here, is not just O, because oxygen, again, is a diatomic molecule. It doesn't just exist by itself. So O2, okay, we're finding the gram formula mass. We only have one element here. There are 2 of them, and each oxygen weighs 16 AMU, or 16 grams. So this comes out to a total of 32, sorry. Let me just get rid of this. This is not my way. So the total mass of O2 is 32 grams or AMU, okay? We're gonna think in grams right now because they're asking how many grams. So now all you have to do is just cross multiply. If this is uncomfortable for you, you can just put this side over 1 and cross multiply. But really all we're doing is just, why does this say 0.2? I am so sorry. It should say 0.5. Again, from right here, 0.5 moles. So 0.5 times 32 will be X. And when you multiply this out, you just get 16 grams. So ultimately, we are going to need 16 grams of oxygen. Again, a 2-step problem. First, you have to do a mole ratio, and then you have to use this equation to go from moles to grams, which is ultimately what they were asking for. Alrighty. Let's get rid of all this. Okay. Moving on to the next page. Let me zoom out a little. Okay. Number 10. So they're giving us this graph, all this info about all of these organic molecules, about all these aldehydes. At the end of the day, they're just asking us to determine the mass of 3 moles of propanol using the molar mass given in the table. So again, when you're trying to go from mass to moles, you just have to use that formula that we just looked at on the reference table. That's the second equation. I'll write it out here for us. So it's moles equals the given mass over the gram formula mass. Okay. So we know moles. They're telling us that it's 3 moles of this stuff. So we've got 3 moles equals the given mass. We don't know that because they're saying determine the mass. So that's just X. And the gram formula mass is, again, basically the same thing as the molar mass. This is nice and easy because they're giving it to us. They're telling us right here in this chart that the molar mass of propanol is 58.1 grams per mole. Again, if it makes you uncomfortable, just put it over 1. We end up just multiplying these 2 numbers. Okay. And what we're going to end up with is about 174 grams. Again, when you multiply these 2 things, the moles cancels out. So you're going to end up with 174 grams. All right. Oh, I just found a way easier way. I cannot believe it took me months to figure that out. But there is a button that just says clear and you can clear all of your drawings. I've been sitting here like erasing everything. You learn something new every day. Okie dokes. Next one. So we are given this unbalanced equation. Okay. And when the equation is balanced, using the smallest whole number of coefficients, what is the coefficient of AL? So what I'm going to do is I'm just going to draw it over here because we're not really given a lot of room. But here we've got AL, pretend that this is the reactant side. So this is over here, and this side is corresponding to the product side. So aluminum, then we've got, let me write this actually a little bit further. So we've got aluminum, we've got copper, sulfur, and oxygen. On the reactant side, we only have one aluminum. We've got one copper, one sulfur, and 4 oxygens. On the other side, we have 2 aluminums. We have 3 sulfurs. Again, that 3 is getting distributed inside. And we have, oh, I should do this in order. Again, you should always do it in order on both sides, so it's just easier to read across. We've got 1 copper, again, 3 sulfurs, and 12 oxygens. So what I'm going to try and do is just fix my aluminums first. So I'm going to put a 2 there. But again, I can't just assume that the answer is going to be 2. I have to balance the entire thing and make sure that later on I'm not going to have to change this coefficient. So now I've changed aluminum to 2. And for now, aluminum is balanced. Copper is good. But you can see here, and here's a little trick, okay? See this SO4? There's 1 inside the parentheses here, but there are 3 chunks of them because of this 3 outside, which means that if I just put a 3 out here, I'll balance this SO4 as well. So now I'll have 3 sulfurs. I'll have my 12 oxygens, again, because this 3 is getting distributed. And I have also changed my copper. Now I have 3 coppers. So now sulfur is good, oxygen is good. The only thing is I need to fix my copper on this side, which is a 3. So yes, 2 was the correct coefficient for aluminum, but I had to balance the entire thing just to make sure that that 2 coefficient is what we ultimately needed, because sometimes you will write a coefficient and then you'll end up having to change it. So just fully balance it and then answer the question. All right. Next one, they're asking us to balance this one. So this one is actually pretty nice and easy. So we have oxygen. This is the oxygen that we breathe, turning into O3, which is ozone. How do you balance this? So we have an even number here and an odd number here. The best thing to do is to literally switch the numbers. Okay. Their common factor or greatest common factor, or I don't think I'm saying that right. They both are, when you multiply them, they equal 6. So try to get both sides to equal 6. Okay, so here we've got 3 times 2. Now we've got 6 oxygens on this side, and this 2 distributes here. We've also got 6 oxygens on that side. So that is all we need, a 3 and a 2 coefficient, and we are done. Look how easy that is now. Okay. Number 13. So we had a question like this before. So the empirical formula of a compound is CH3. So our ratio here is 1 to 3. We need to know what molecular formula could this have come from. So we need to find one of these has to have the same ratio, 1 to 3. So this one right here, this is 2 to 6, but we can reduce this because both are divisible by 2. So it would end up being 1 to 3. So this is the one that we're going to go with. All right, next one. What is the total mass of iron in 1 mole of Fe2O3? That's iron 3 oxide. What they're really asking you, because specifically they're saying 1 mole, is they're basically just saying, what is the molar mass? So let's just figure the molar mass. Okay, so we've got iron, we've got 2 of them. Oxygen, we've got 3 of them. The mass of iron is 56. You can go check it out on the periodic table. Mass of oxygen is 16. Go ahead, multiply everything out. That's 48. And when we total this up, okay, this is going to be 160. So that's the molar mass. Oh, actually I made a mistake. No, they're not asking for the molar mass. My bad, that was a mistake. Okay, so this is the molar mass, but what they're asking is what is the total mass of just the iron in this compound? We can see that the total mass of the iron in this compound is 112. So they kind of trick you by putting that 160 there. All right. Let's move on. Next page. Okay. 15. So they're asking us to balance this equation. So they really don't give there's really not a lot of room here. Okay, but on this side, we've got phosphorus, we've got 4 of them. Oxygen, we've got 10 here, and then we've got 1 there, so that's 11. And then hydrogen, we've got 2. On this side, we've got 1 phosphorus, we have 4 oxygens, and hydrogens, we've got 3 of them. Now, the easiest thing would be to balance, let's see. Yeah, easiest thing to balance right now is the phosphorus. So this side needs a 4, okay? So when I do that, now I change a lot of stuff. So now I have 12 hydrogens. I've got 4 times 4, that's 16 oxygens. And now I have my 4 phosphorus. So now my phosphorus is good, okay? My oxygens and my hydrogens, not so good. So what I'm going to do is I'm going to try and fix, the easiest thing to fix right now is my hydrogens. So I've got 2 on the reactant side and 12 over here. So this needs a coefficient of 6. When I do that, okay, now I've got my 12 hydrogens, so that's good. And now let's look at also what's happened to oxygen. I have 6 oxygens coming from this, but I also have 10 over here. So it's really 10 plus these 6, that is 16. And that is it. Those are my coefficients that I need. Again, you can write the 1, but really you don't need to. All right, next is write the empirical formula of the solid reactant in the equation. Now let's say that you forget, if you get to this question, you can't remember, oh man, which side is the reactant? They're telling you that the thing is a solid, and there's only one solid here. So you know that they're talking about this thing. So we're given this molecular formula, P4O10. And they want the empirical. So you need to reduce this. 4 and 10 are both divisible by 2. So divide this by 2, divide this by 2. That's 2 and 5. So you just use these numbers and rewrite your equation. So it would be P2O5. That's it. Next, show a numerical setup. Again, be on the lookout for this numerical setup. They're not actually asking you to solve it and give them a number. They just want the setup. So show a numerical setup for calculating the percent composition by mass of phosphorus in P4O10. This one's nice because they're already giving you the formula mass. So all you have to do is just at this point figure out how much 4 phosphorus weighs. So phosphorus is 31, but there's 4 of them, so that's 124 U. Again, to set up for percent composition, it's always the part over the whole. So 124 U over 283.89 U. And then again, it is percent. So you have to multiply the whole thing by 100%. And this would literally be your answer. But you actually don't even really need to put the units. This would be totally fine. Also, what would have been acceptable would have been, instead of putting the 124 and multiplying them out, you can do even less work. And you can actually just say that you have 4 times the mass of phosphorus. This also would have been acceptable. So either one is fine. All right, number 18. Which equation represents a conservation of atoms? When they're saying conservation of atoms, they're basically asking you which one of these is properly balanced. So let's look at choice A. In choice A, we have 4 irons. That's good. Over here, we have 4 irons. That's good so far. Here we have 4 oxygens, but here we have 6 on the product side. So this is no good. Other side, 4 irons here, 4 irons here. That's good. We've got 6 oxygens here, and this 2 will distribute, and we also have 6 oxygens. So this is our winner. This one is properly balanced. If you check the other 2, C and D, they will not match up on the reactants versus the product side. You guys can check that out yourselves if you want to. It's good to always go through all the options just to make sure. Okay, number 19. What is the percent composition by mass of aluminum in aluminum sulfate? Now, some questions will give you the gram formula mass. They'll be nice and they'll give you that. Sometimes you have to figure it out on your own. So it'll sort of be like a two-step problem. But they're giving it to us, which is nice. So again, it's always the part over the whole. So we have 2 aluminums, and each one weighs 27. So the total weight of the aluminum is 54 grams. So it's 54 grams for just the aluminum, but the entire compound is 342 grams. Okay, so you divide these and you multiply by 100, and you should end up with 15.8%. Again, you divide these two numbers and then multiply by 100. All right, 20. What is the total number of moles of carbon monoxide used to produce 112 grams of iron? Well, first, what we should do, because again, equations, balance equations are always in terms of moles, but they're giving us not moles of iron, they're telling us the amount of grams of iron. So what we should do is we should figure out, well, how many moles is 112 grams of iron? Okay, so we can use this equation. Moles equals mass over gram formula mass. Now this one is actually really nice and easy because they're giving us the mass. So I'll erase this. Sorry, my windows are open. Okay, so the given mass is 112 grams of iron. And the gram formula mass of iron is real simple because it's just iron. So it's literally just the atomic mass that you see on the table, which would be 56 grams. You divide these, and it ends up just being 2 moles of iron. So this is how much iron we are trying to produce. Okay, so this is sort of like the other problems where it's 2 steps, but you're kind of working backwards here. So what is the total number of moles of carbon monoxide used to produce 2 moles of iron? Now you have to look at the mole ratio. So here you've got 2 moles of iron and 3 moles of carbon dioxide. So 3 moles of carbon dioxide make 2 moles of iron. So we literally don't even have to do any math here. They're telling us the answer. In order to make 2 moles of iron, you need 3 moles of CO, or carbon monoxide. All right. Number 21, a compound has a gram formula mass of 56 grams per mole. What is the molecular formula for this compound? So this is just like, you got to just plug everything and figure everything out. So you have to just figure out the gram formula mass of all these things until one of them is 56 grams. So I can see here, I've got carbon, I've got 2 of them. So carbon, 2 of them, each one is 12. Hydrogen, there's 4 of them, each one is 1. This will total out to 28. So it's not A. Choice B, we've got 4 carbons, each one is 12. So that's 48 coming from the carbon. And 8 hydrogens, that's just a total of 8 because each one is 1. And you add this up and this is 56. So it's going to be B. You can also do the same. You can find the gram formula mass for C and D, and you'll see that it will not equal 56. You can try that out on your own if you wish. Okay. 22. We're given this reaction, this balance equation. What is the total number of moles of O2 required to produce only 1.5 moles of CO2? So again, circle the ones that they're talking about and then do the same in the formula. So from my formula, or from my recipe, you can think of it as 5 moles of O2 make 3 moles of CO2. But we don't want 3 moles of CO2. We only want 1.5 moles of CO2. And again, make sure your substances always match going across. So we're looking for how many moles of oxygen are going to be needed in order to make this serving size. So you go ahead and you cross multiply 5 times 1.5. That should be 7.5 equals 3x, divide by 3. And we should end up with x equals 2.5. So we are going to go with choice B. Okay. Right, let me clear this. All right. 23, given this structural formula, what is the empirical formula of this compound? So from the structural formula, we can figure out the molecular formula. So there's 1, 2, 3, 4 carbons. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. And there's 1, 2 oxygens. Now, this is the molecular formula for this compound. We want to know what's the empirical formula. So you have to find a number that all of them are divisible by. They're all divisible by 2. So our new numbers would be 2, 5, and just 1, but we don't write ones. So it would just be this. So we would end up with choice D. Okay. Next, the molecular formula of glucose is C6H12O6, and we want to know what is the empirical formula. All of these are divisible by 6. So divide everything by 6. You'll see your new numbers are 1, 2, and 1. So rewrite everything. But again, you don't write 1. So we would really rewrite this as CH2O. And again, choice D. All right, number 25. Again, another empirical formula question. Write the empirical formula for this compound. Start off by writing your molecular formula. So we have ethyl ethanoate, we have C4, there's 4 carbons. There is 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and I see 2 oxygens. These are all divisible by 2. So our new numbers would be this. Again, no 1, so you can just leave it like that. This would be your empirical formula. Okay, number 26, which type of reaction is represented? So here I can see I'm starting off with an element, E, and I'm starting off with a compound. I also end off with a compound, and this should be over here, but I guess it got cut off. We end off with an element. If you start off with an element and a compound and end up with an element and a compound, that is like the general formula for a single replacement reaction. But also you can just take a look at what happened. Here you have magnesium by itself, and then on the other side, the magnesium took the place of the silver. The silver got kicked out. So one thing in the compound got replaced. So this is a single replacement reaction. Number 27. The total number of grams of Cu needed to produce 1 mole of copper 2 nitrate. So again, you're seeing grams mixed in with the word moles. So you know that you're going to have to eventually use this formula. So I'll just write it over here. Moles equals mass over gram formula of mass. So I know at some point I'm going to have to use this. Okay. Now we have to figure out our mole ratios. So I'm going to circle everything I've got. I've got copper. I've got copper 2 nitrate. I'm going to circle these things in here. Now this one is kind of easy because 3 moles of copper makes 3 moles of copper 2 nitrate. So the ratio is just 1 to 1. So if you need 27 moles of copper, it's going to make 27 moles of this. You don't really need to set up a proportion. So if we're using if we end up with 1 mole of this, it means that we started off with 1 mole of copper as well. If you want to see the setup, we can do that. 3 moles of copper makes 3 moles of copper nitrate. But we don't actually end up with this many moles. We just end up with this many. How many moles of copper did we start off with? If you cross multiply, you'll see that the answer just comes out to be 1 mole of copper. So now what we need to do is we need to convert 1 mole of copper into grams. We want to know how much does it actually weigh. So we know the moles. I'm going to erase this. This is just 1. What's the gram formula mass of copper? If you go to the periodic table, it's like 63.546. You can just round, I guess they were just rounding it to 64. And this here is X. So if you cross multiply, you'll see that X is just 64 grams. So 1 mole of copper, 64 grams. Okay, number 28. Which change results in the formation of different substances? This different substances being formed, that's a chemical reaction. So A, Deposition, that's a physical change. Melting, physical change. Burning is a chemical change. You can't unburn something. Solidification, that's another way to say something is freezing. So that's also physical. So we're going to want to go with choice C. Burning, this is combustion. Okay, combustion is one of our chemical reactions. Again, in a combustion reaction, you always start off with some organic compound, like propane, expose it to oxygen, and you end up with your two products of every combustion reaction, which are carbon dioxide and water. Oops. Okay. 29. Given the balanced equation representing a reaction, what is the mole ratio of CO to CO2 in this reaction? So the ratios just come from the coefficients. So I'm just going to circle what they're talking about: carbon monoxide versus carbon dioxide. And I see here that the ratio is 2:2. So 2 moles of carbon monoxide will make 2 moles of carbon dioxide. And so if we just simplify this, this just ends up being a 1-to-1 relationship. All right. Number 30. What is the gram formula mass of potassium carbonate? So again, for this, what you do is you write out all the elements that you see, count how many you have. We've got 2 potassium, we've got only 1 carbon, and 3 oxygens. Then you would go to your reference table, to the periodic table, look up their masses. You'll see that potassium is 39, carbon is 12, and oxygen is 16. Okay, so you can multiply all of this out. This is 78, this is 12, that is 48. You add everything up. This is 8, carry the 1, 138 grams. So we're going to go with choice C. Okay. So we're given this reaction here. What type of reaction is shown above? So I can see here, I start off with copper, an element by itself, and a compound. And on the other side, I also end up with a compound and an element. Again, this kind of signifies to us that, or shows us that we are going to have a single replacement reaction. So what we see here is that H, or hydrogen, got booted out of the compound and copper took its place. Now, again, typically a metal will replace a metal and a non-metal will replace a non-metal. Now, hydrogen is technically a non-metal. However, it can sort of act like a metal or a non-metal because of hydrogen's electrons. So, or its electron configuration. So hydrogen has just one electron. So what it can do, again, remember our Bohr model, our first ring can hold 2 in total. Now, hydrogen can do 2 things to kind of be stable. What it can do is it can bond to something else, okay, gain another electron, so that we'll have a full first shell with 2 electrons. Or what it can do is it can lose this electron, much like a metal would do. And then hydrogen would have no electrons at all. So this first shell would really be empty. But even though it's empty, we would still consider hydrogen to be stable. So again, hydrogen can sort of act like a metal or a non-metal, just depending on really what you put it with, okay? So in this case, the metal, copper, is replacing a non-metal, hydrogen. Just remember that hydrogen can sort of act like a metal sometimes. So this, again, is a single replacement reaction. All right. 32. Which pair consists of a molecular formula and its corresponding empirical formula? So let's just look at the first one, P4O10. So this is our molecular formula. If we were to write our empirical formulas, I see that both of these, sorry, this should be gone. They're both divisible by 2. So if I were to rewrite them, it would be P2O5, which does match to what they're giving us. So it is going to be A. But let's just take a look at B, just as an example of why the other ones don't work. So C6H6, that's the molecular formula that they're giving us. And if we were to reduce this and simplify it, it would just be CH, because both are divisible by 6. So, and that's not what we're seeing here. So that doesn't work. And if you look at the other ones, you'll also see that they do not work. All right, 33. What is the gram formula mass of sodium carbonate? And this O should be over here, so it's really H2O. Now, what this means, and you might see this sometimes, okay? What this means is that you have this ionic compound being hydrated or surrounded by 10 water molecules. So this is known as a hydrate. Okay, again, an ionic compound that is sort of connected or being surrounded by several molecules of water. Now, to find the gram formula mass of this thing, all you really need to do is just find the mass of this, find the mass of water, okay, multiply that by 10 and add all of these things up together. So we're going to do that right now. So first, I'm going to just focus on the sodium carbonate. So I'm going to do that over here. So I have 2 sodiums, I have 1 carbon, and I have 3 oxygens. So if I find all their masses, these are the masses I will find on the periodic table, multiply everything out and add everything up. This comes out to 106 grams. Okay, so the sodium carbonate alone is 106 grams, but it's not by itself. It is attached to 10 molecules of water. So what I'm going to do is I'm just going to find 1 molecule of water. In 1 molecule of water, there are 2 hydrogens, there is 1 oxygen, multiply by their masses. Oh, that should be 6. And the total mass of 1 molecule of water is 18, but I have 10 of them. So I'm just going to multiply this by 10. And that's 180 grams of water. Now, again, we're asking for the total mass. So this and this need to be added together. So it's 106 plus 180. That comes out to a total of 286 grams. Again, this is called a hydrate. We'll actually have a lab based on this idea. Okay. Number 34. This information can be found in lesson 9.3. Which quantities are conserved in all chemical reactions? That is going to be charge, mass, and energy. All 3 of these things must be conserved in any chemical reaction. 35, so another balancing question. Okay, so what is the coefficient of O2 when the equation is balanced correctly using the smallest whole number coefficients? So I am going to rewrite this actually, just because it will be easier for us to see. Okay, and now I will split this in half. We have Mg, we have Cl, and we have O. We should have the same stuff on the other side. Here we have 1 magnesium, we've got 2 chlorines, and we have 6 oxygens. Again, this 2 gets distributed into everything in the parentheses. Here we have 1 magnesium, 2 chlorines, and 2 oxygens. So what I'm going to try and fix is just the magnesiums. Okay. So all I have to do is just fix my oxygens, and this side is just going to need a 3. That is it. And we are now balanced. So this is a very nice and easy balancing question. And they're asking what's the coefficient of O2? It is going to be 3. We just put a 3 here. That's it. Okay, nice and easy. Next, what type of reaction is shown above? Again, another example of a synthesis reaction. 2 separate substances coming together or combining to form 1 larger compound. Okay. 37, which equation represents a double replacement reaction? So here, what I can see is that lithium and hydrogen have swapped on the other sides. Okay, so this hydrogen right here will take the place of lithium. So that means we're going to have HOH, which is really this guy right here. We've got H2O. So that's how we get that. Now, lithium booted this hydrogen out and took its place. So the Li and the Cl come together. So I'm just going to say this, it's not necessarily true. The two metals have switched places. Again, hydrogen is not really a metal, but in this case, it is sort of acting like it, okay? So the lithium and the hydrogen, they switch places, and this is considered a double replacement reaction. Okay. If you look at the other ones, this looks like a singular replacement reaction, C looks like a decomposition, and D looks like a combustion reaction. Okay, so yes, we would want to go with choice A. Number 38. What is the maximum number of moles of water that can be produced when 2 moles of NH3 are completely reacted? So moles, moles, moles. So here's another mole ratio. Again, I'm going to circle whatever they are talking about here. So H2O and NH3. I'm going to circle these things as well and just pretend like the other stuff doesn't exist, basically. So from my recipe or my equation, I can see that 4 moles of NH3 will make 6 moles or 6 servings, you can think of it as, of water. However, I don't have enough ammonia for this recipe, okay? I don't have 4 moles of NH3. I only have 2 moles of NH3. So how much water is this going to produce? I know that since I don't have this much ammonia, I also shouldn't get 6 servings of water. So I know that my final answer should definitely be less than 6. Again, whenever you're dealing with numbers, make sure your numbers make sense. Think about the types of numbers that you should be getting. So right now we just cross multiply. So it's 4x equals 12 divided by 4 and x equals 3. That's it. Okay. Number 39, which list consists of types of chemical formulas? Number 1 doesn't make sense. That's classifying the elements. Atoms, ions, and molecules, those are not types of formulas. C, empirical formula, molecular formula, structural formula. Those are all formulas. That's good. D those are all types of reactions. Those are not chemical formulas. Those are chemical reactions. So we're going to want to go with choice C. Again, I'm going to give you an example actually of all these things just so we have it fresh in our minds. So let's draw ethene. So here is a structural formula. It shows you the structure or the shape of the molecule. Our molecular formula simply tells us how many atoms and elements we have. So we have carbon, there's 2 atoms. We have hydrogen, there's 4 atoms. This is the molecular formula. This tells us exactly what our compound contains. Now, our empirical formula is our molecular formula reduced to the smallest ratios. So for this, it would be CH2. So structural, molecular, empirical. Okay, 40. Which quantity is equivalent to 39 grams of lithium fluoride? Now they're giving me grams and the answers are all in moles. So that means I need a mole to mass conversion, which means that I'm going to need this formula again. Moles equals mass over gram formula mass. Now the number of moles, that's what we don't know. So this is X. The mass they're telling us is 39 grams. So just plug in 39 there. 39 grams. The gram formula mass, they're not telling us. So we have to figure it out using this. So lithium fluoride, if you go to the reference table, lithium, we only have 1. The mass, I believe, is 7, I think. And fluorine is 19. So it's 7 plus 19, that is 26 grams. So this is the gram formula mass. It is 26, this should say per moles. So it is 26 grams per mole. We're going to divide these. When you divide, the grams cancels out, and you end up with 1.5 moles of lithium fluoride. So we're going to go with choice D. Okay. Next, 41. How many moles of oxygen are needed for the complete combustion of 3 moles of CH4? So again, moles to moles, so mole ratio. So I'm going to circle again whatever they're talking about in the problem, oxygen and methane. So I'm going to do the same thing here, methane and oxygen. I'm going to set up my left side of my proportion. just using my original recipe. So 1 mole of methane reacts with 2 moles of O2. That's our recipe. Okay. Now we want to know how many moles of oxygen are we going to need if we start off with 3 moles of methane. Again, make sure everything matches going across. So you just cross multiply, 1x equals 6. So that's just x equals 6 moles. So it's choice A. Okay. Number 42. What is the total number of moles of carbon that must completely react to produce 2 moles of, that looks like ethane. Ethane. Okay. Again, moles and moles. So another ratio. So they're talking about carbon and they're talking about ethane. So I'm going to circle these 2 things. I'm going to set up my proportion. 2 moles of carbon will make 1 mole of ethane. However, this serving size is not good. We don't want that. That's not what we want. Okay, we want 2 moles of it. So we want 2 moles of ethane. How much carbon are we going to need? So you cross multiply and x turns out to be 4 moles. Okay. Next, 43. Which term identifies types of chemical reactions? So we look at choice A, decomposition, synthesis. These are both chemical reactions, so that works. But let's just look at the other choices. B doesn't work because deposition is a physical reaction. C, deposition, sublimation, both physical. D, decomposition is good, but sublimation, physical. So none of these work. All right. Number 44. Which 2 solutions, when mixed together, will undergo a double replacement reaction and form a white solid substance? Now, a white solid substance, okay, this is basically what's happening is in order for a double replacement reaction to occur, one of the products needs to be insoluble in water, meaning it doesn't dissolve or mix well with the water. And so it will literally form into a solid and probably end up sinking to the bottom of the beaker or the test tube, whatever you have it in. And this solid substance that is insoluble, we refer to it as a precipitate. And we say that it precipitates out of the solution. So what we have to do is this question is a little bit of a challenge because we need to first figure out what are the products here. In the choices, they're not giving us the products. They are giving us the reactants. So they're saying, when, for example, choice A, when you mix sodium chloride and lithium nitrate together, will this reaction actually work? Will one of the products give you a white solid substance? Will one of the products be insoluble? So first you got to figure out your products. Now, what you do is you take your metals and you switch them. So Li is going to take the place of sodium. So the Li is going to be with the Cl. So we have lithium chloride. Again, the metal always goes first. And we're also going to end up with this sodium is going to take the place of the lithium. So we're going to end up with NaNO3. Now, at this point, what you need to do is you need to, I'm going to erase this stuff. We need to go to the reference table and we need to go up to table F. This is solubility. Okay. Now here, again, I'm just going to write out what my products were for that reaction. It was LiCl and NaNO3. I can see right here, anything with Li or anything with Na, they're both soluble. So this reaction doesn't work. Again, at least one needs to be insoluble. So it's not A. B, we have to, again, first figure out what our products are going to be. So we are going to have potassium and silver switch. So the silver is going to take the place of the potassium. So Ag will be with Cl. So we've got silver chloride. And we're going to end up with potassium nitrate. Now let's go back here. And again, our 2 products here are AgCl and KNO3. Now, potassium is also in group 1. So it's in this section. But in case you don't look that potassium is in group 1, you can see anything with nitrate is also soluble. So this thing is soluble. Now we have to look at AgCl. Okay, so I see Cl, this is a halide. Cl, or chlorine, is typically soluble, except if it's with silver. So we have one of the exceptions. So this thing is actually insoluble, and silver chloride will form a white solid substance, and it will fall to the bottom. So our answer is going to end up being choice B, because one of the products of this reaction is going to be insoluble. All right, number 45, the approximate percent by mass of potassium in KHCO3. Okay, we have to first figure out the total mass of this. So we have K, H, we've got C, we've got O. So we've got 1 potassium, we've got 1 hydrogen, we've got 1 carbon, and we've got 3 oxygens. Okay, now go to your table. Give me 1 second, guys, sorry. Okay, so potassium is 39, oxygen is just 1, chlorine is, we'll say about 35, and oxygen is 16. So we add everything up, and it actually comes out to 100 grams. Oh, wait. Oh, no, I am so sorry. I read that as Cl instead of 1 carbon. Brain fart. Okay, this is 12. Now this should add up to 100. Or it should. Let's see. Does this work? Oh boy, guys. I'm getting tired here. That's what's going on. I'm so sorry. Let's do this step by step, because clearly I need to. Okay, these are all of our individual masses of all our elements, and it should add up to 100 grams. And they're asking for just the potassium. So total mass of the potassium in the compound is 39 out of 100. And then if you just multiply this by 100, it just ends up being just 39%. Okay. All right, clear this. All right, number 46, explain in terms of substances why the reaction is a decomposition reaction. So I can see here we've got hydrogen peroxide being broken down into water and oxygen. So you can say one of two things. You can say that one substance, I'm going to write this down, one substance reacts to become 2 different substances. This is a fine answer. You can also say that a compound becomes a smaller compound, basically, or just becomes a compound and an element. So it's breaking down. So those would both be acceptable answers. All right, number 47. The formula H2O2 is an example of, this is a molecular formula. It's not empirical because if it was, it would just be H and O, but it's not. It's also not an organic one because there's no carbon here. It's not ionic because these are both nonmetals. Number 48. What is the percent composition by mass of oxygen in calcium nitrate? So they're being nice. They're telling us the total mass, that's 164. We just need to know what's the total mass of the oxygen in the compound. I can see that there's 6 of them, and each oxygen weighs 16. So that is 96 grams in total from the oxygen. So 96 over 164 times 100. And we should end up with about 59%. So calcium nitrate is 59% by mass oxygen. Okay. 2 more. All right, 49. The percent by mass of oxygen in sodium sulfate. So same sort of concept here. They're giving us the total mass, so that's nice. So the total goes at the bottom, that's 142. The total mass of the oxygen, we have to figure, there's 4 of them each way, each one is 16, so that's 64, so that goes on top. Again, part over the whole, times 100. And our final answer is going to come out to about 45%. Okay, last question. What type of reaction is shown above? Here is another single replacement reaction. This one just might look a little weird because the element that's by itself is a nonmetal, but the nonmetal will replace the other nonmetal. So the fluorine is going to boot out the bromine, and you can see that it takes its place. So again, a single replacement reaction. And again, to decide if a single replacement reaction will work, the element that is by itself needs to be more active than the thing it is trying to kick out of the compound. Okay, and that can be found on table J. So I hope that this was helpful. Again, if you need help with a specific idea or a specific topic, and you feel like this review didn't really help you with that, you can go onto my website and you can go to either the section with exam reviews, or you can go to the guided notes section for this unit, and you can check out all of the individual YouTube videos that I have posted. But guys, happy studying and good luck.